All right, so we're talking about now in 6.3 volumes. And by volumes, we're not meaning like auditory levels, like tenths of the unit bell, named after Alexander, right? I wonder why we always measure it in decibels and not just bells. Why didn't they just recalibrate the unit and call them bells? We have to always measure in a tenth of that unit. I don't know. Anyway, I wasn't there. Just as area is always positive, so is volume and our attitudes towards finding it. Okay. Let's review how to find the volume of geometric prisms. My daughter's in 7th grade. She's doing this right now, Schroeder. Finding volumes of geometric prisms. How do you find the volume of a geometric prism? We have right here a rectangular prism on the left. The next one would be a triangular prism. The next one would be another triangular prism. And the third one would be a circular prism, which we call a cylinder, right? So all you have to do to find the volume of a cylinder is to find the area of the face, which sometimes is called the base. I think on the tax EOC chart it's called the base. You have a base at the top and the base at the bottom, and then all you have to do is multiply by the distance between the two faces. Okay, so that would be that. Here you can find the area of the face, or the base, whatever you want to call it, which is facing you. It's not necessarily always the base. And you have one at the back, and then you just multiply by h, the distance between them. Yeah? Same thing here. Same thing here. We've already done this, cylinders. The area of the face would be a circle. And here's another circle on the bottom. It's like a stack of coins. And all you got to do is multiply by the distance between the two. And the volume, of course, would be the area of the face, which is pi r squared, times the height, which is h. That's the volume of a cylinder. That's where it comes from. So in this section, cross-sections of three-dimensional objects that have known geometric formulas for area, we can find the volumes, as I mentioned in the previous section, if I can somehow come up with an area formula in terms of a single variable. I can multiply by an infinitely thin slice, which would be end up being the height, and that is going to end up being dx. So if I can come up with the formula for the area of the cross-section, then the distance between the two faces could be infinitely thin. If I just added all those up from A to B, I'm going to end up with the volume of the region. That's where we're going with this. Okay, so imagine slicing a loaf of bread mathematically. It might look like this. Here's a piece of bread. All right, you take a slice out of it. You want this slice right here. Well, if you could somehow find the formula for the area of the face of that piece of bread, the one that you would butter or whatever, the thickness of that piece of bread would depend on how thick you sliced it, right? Now, if you're in Texas, you probably slice Texas toast, right? And you have a pretty big delta X, right? Texas, everything's bigger, including our slices. Well, that would be some kind of geometric prism, right? You would have a face that is shaped similar to the one in the back, and the thickness delta X would be the height, the distance between them. Now, notice because the top is curved, you don't have a true geometric prism, because if you notice where I'm slicing it here, the area of the face in the front should be a little bit bigger than the area of the face in the back, simply because my curves are going down, right? So how can I eliminate the error if I was to find the volume of this by taking the area of the face times delta X? I can make delta X smaller. I can slice in Texas still, but just maybe a little bit Rhode Island style. If I slice it a little bit thinner, now, but there still should be some error. Well, let's slice it thinner yet. If you slice it super, super thin, what's going to happen to your sandwich? It's going to look like a meat sandwich, right, with no bread. Right? It says, I promise you, there's a thin layer of bread on the top and bottom. The thinner the slice, the closer you get to the areas of the front face and the back face being the same. Well, the difference between a delta X and a dx, remember, is that dx is an infinitely thin, non-measurable delta X. Okay, and that's the calculus part. But the idea behind what we're doing here is if I can basically find the volume of each of these slices of toast. okay? If I can find the volume of each of those slices of toast, I can add the volume of each of those pieces together and get an approximate volume for the whole loaf, right? Find the volume of this slice, this slice, this slice. Those are all Texas toasts. Add them together, and I can get an approximation for the volume. The thinner that I make my slices, if I made those just half as thick, then I can add all the volumes together, the more accurate it's going to be. And finding the volume that way is a lot better than liquid displacement or fluid displacement, right? Because you don't want to find the volume of a loaf of bread by displacing fluid, because then the bread gets soggy. Okay? So we want to find it using calculus. Now, you see a limiting process here, right? As the thin slices get more and more and more, or the slice thickness gets smaller, the number of slices approaches what? Infinity, right? And the approximate volume ends up approaching the actual volume. So the key here is this. Can I find a formula for the area of the face as a function of a single variable x, in this case, where I am on the coordinate plane? Because if I can do that, all I got to do is multiply it by dx and then add them all up from left to right. All right, we have 10 minutes. Here's the definition of the volume of a solid. Let S be a solid that lies between two vertical lines, x equals a and b. If the cross-sectional area of S in a plane through x perpendicular to the x-axis, basically, if I can find the area of the cross-section when I slice it vertically, where A is continuous, then the volume is going to be the limit as the thickness of the slice delta x goes to 0 of the sums of all the areas of the geometric prism's face times the height between them, which is delta x. That's going to equal the definite integral of a of x dx. All right, so if I can write it in this form, then I can integrate it and use the fundamental theorem of calculus to find a volume, a three-dimensional quantity. All right, example 1, and we'll finish for the day. The volume formulas for the shapes shown at the top of this lesson and the others from your geometry class, or that we came across in the related rates and optimization sections, they're all derived from calculus. They didn't just fall out of the sky one day in one big bundled package. Let's show that the formula for the volume of a sphere, by the way, is what? Without looking, what's the formula for the volume of a sphere? 4/3 pi r cubed. That's the formula for the volume of a sphere. Here's how we're going to do it. I'm going to draw a sphere right here, a cross-section of a sphere. It's three-dimensional. See that? Three-dimensional. I slice it right through the middle. The radius of the sphere itself is little r. So we're going to call that little r. Now, let's kind of imagine that it's coming like this, you know. What I want to do is take a slice out of this sphere. I want to slice it right here. Okay, that's my knife cutting right through. And I'm slicing it dx thick right here. So I'm taking a little dx slice out of there. And notice the top curve is a little bit angled, and so is the bottom curve, right? So if you're approaching it from the left, the circle is a little bit bigger on the left side than it is on the right side. You see that? If I were to pull that slice out and stare at it head on, it would resemble a what? It would look like a circle, right? Here's my dx thickness that I pulled out. It would look like a disc, right? All a disc is, it's a squatty cylinder, right? That's all it is. Look what you could do with Notability. You can lasso it with scissors. You can turn it like that, and now it looks like a squatty little cylinder, a right circular cylinder, whose height is dx, right? And all we have to do is come up with the area of the face and multiply by the height. So here we go. The volume of that little slice is going to be the area of the face times the height. Well, what's the area of the face? What shape is it? It's a circle, which is pi r squared times h. Now, here's the thing. I can't use little r there. You know why? Because little r is we're treating it like a constant. It's the radius of the sphere. The radius of my slice is going to vary. If I slice it really close to the end, I'm going to get a little piece of bread. If I slice it closer to the middle, I'm going to get a bigger piece of bread. This is what the radius is, right? I'm going to call it big R of x. Big R of x, or big radius. That's going to end up being this right here, big R of x. Now, if I can write the equation, essentially for big R of x, I can plug it into pi r squared, and I'll have the formula for the area. Well, big R of x is pretty easy to find the equation for, because if you just look at this is a semicircle, and the equation of that semicircle is just the square root of the radius squared minus x squared. That's the equation of a semicircle. Where r is the radius of the sphere. So here we go. I can now say then the volume of that little slice is pi times big R squared. Well, what's big R? It's going to be the top curve minus the bottom curve. The top curve is square root of r squared minus x squared, and what's on the bottom here? The x-axis, right? Which is y equals 0. So I can substitute that in there, the square root of r squared minus x squared times my height, which is really going to become dx. So here we go. The volume of the whole thing. All I have to do now is add up my slices all the way from left to right, which is going to be from negative r to positive r of this equation here, which is pi times, notice the square root of that squared just becomes r squared minus x squared, and then of course h becomes dx. Now, I can also use symmetry here. I can pull the pi out front. I'm going to double it from 0 to pi instead of going from negative r to r. And now I got r squared, which I'm treating like a constant, minus x squared. Now we're running short on time, but I'm going to keep going here. The 2 pi now goes along for the ride. I've been able to express my area of the face as a function of x, little r is a constant, and then times dx. So what's the antiderivative of little r squared with respect to x? Well, it's r squared x, because r squared is a constant, minus 1/3 x cubed. I evaluate it from 0 to pi. 2 pi goes along for the ride, and we get, plugging in for x, we get r squared times pi, so pi r squared, minus 1/3 pi cubed. Uh-oh. What's that? Yeah, it is 0 to r. I put pi there. That's, oh my gosh, yeah, that's me just feeling the clock and making a stupid mistake. I'm sorry. 0 to r, yeah, we don't put pi there. It's still 0 to r. So we got 2 pi. Thank you, thank you. Uh-oh, we got a minute left. Let me calm down. 0 to r, not 0 to pi. So now we plug in an r for x, and we get r cubed minus 1/3 r cubed. That's plugging in the top. And when you plug in a 0 for x, you get minus 0. Now, simplifying on the inside, you got 1r cubed minus 1/3 r cubed. That's going to be 2/3 r cubed. And if you multiply, you get 4 pi thirds r cubed. And there's the volume. And notice, since we treated little r like a constant all the way through, we can now, at the very end, let it vary again, and it becomes a formula for the volume of a cube for any sphere whose radius is little r. Nice. There you go. We just derived it. Kind of anticlimactic with that little error at the end, but that's kind of the idea. We're going to learn how to apply that generally for functions starting tomorrow. So worksheet for 6.2 due tomorrow. We'll have a little area quiz tomorrow too.